Slowly drifting by. Hello everyone, I'm back. It's Friday and we're actually doing the x86 decoder stuff that I had planned to do yesterday, but just had a lot of work yesterday and wasn't feeling up to doing the stream, so we are shifting things back a little bit. I will do x86 decoder today, probably more binary exploitation practice tomorrow, and then we'll just maybe do one day of try hack me on Sunday. We'll see how I'm feeling. Maybe I'll do a longer stream of try hack me on Sunday, make up for it or something. Yeah, so working on the x86 decoder today, and I've just been looking at this chart before the stream started, trying to come up with a plan for what instructions I want to work on next. I remember I had a thing that I wanted to fix on a that I talked about a little bit on the previous stream, so I'll definitely probably start with fixing that issue, which is some of our, or anytime we're decoding a mod RM and a SIB, we need to keep track of what the operand size is, because it didn't come up in any previous tests, but one of the tests that we added at the end of the last stream, I think it might have been this one, where maybe it was this one. We have because we're doing an SIB, we are using the 32-bit versions of registers, but the actual address, like the size of memory that this calculated address is actually referencing, is a single byte. That might be true for both of these. I'm going to run it with Zydus FE8C B2 1F. So certainly it's true for this one. It is a byte pointer composed of these parts from the SIB byte. The issue, though, is there's nothing that we have in our instruction output that actually determines that this needs to be a byte pointer. A lot of the previous ones we could, I think, like we could infer that based on the second operand, for example. We wouldn't be moving 4 bytes of an immediate value into a single byte memory location, for example. So you could probably look at all the data in this instruction and work out that the memory reference from the mod RM was 32 bits, was a D word, because I'm pretty sure that is the case here. 81 B90A 01020304. Yeah, it's a D word pointer. So you could work that out just because we had a 32-bit immediate. This one, maybe not, because I think you could actually, no, I think if you have a 8-bit immediate, it is definitely going into a 32-bit memory, or I'm sorry, if you have an 8-bit immediate, it's definitely going into an 8-bit memory location. It's going, the other operand is going to be a byte pointer. So I think in all the previous registers, we could basically figure out that the pointer side was a D word or a byte based on the other operand. But in this case, we have some that are single operand instructions, like increment, decrement. And when they're doing a memory reference, we need to be explicit about what the size of that memory reference is. And I think we should just be explicit about it everywhere, because it doesn't, having to infer this because the other operand is a certain size just adds more complication that's not necessary and introduces the possibility of doing that wrong. So I think we should simply have a field on the SIB version in the mod RM version of an operand structure that says what the operand size is. Linus didn't make Linux. Hey, how's it going? Thanks for joining the stream. Cool. So I'll probably do that. It's gonna be kind of boring stuff because I'm just gonna like add an entry into all of these tests, but I don't know. I've only been working on this on stream, so I'm probably gonna keep with that, and so it's gonna happen on the stream, even if it's not maybe the most exciting bit of work. But after that, because I don't imagine that is gonna take more than 20-30 minutes at the most. I think it should be obvious what stuff I need to add to the test, and I think I can just set that value based on like the W bit anyways, so it shouldn't be very hard to implement. So for the rest of the stream, we're going to be adding more instructions, and I've just been trying to come up with what is a reasonable plan, because I think we are rapidly running out of the low-hanging fruit in terms of groups of instructions that are encoded in relatively clear or like obvious ways. I don't know how to present it, but like this chunk of instructions all sort of operating the same way and being encoded in the same blocks just makes the opcode parsing for them a lot simpler to achieve. It's a lot more regular, and so I don't have to write a bunch of custom like if cases and stuff that just look kind of nasty. And then we did the inc and dec, which are, they occupy this entire row with the 4 as the upper nibble of the opcode byte. So that was pretty good. And now I think I'm going to do push, and we also have pop. So we can do push and pop, and maybe that's going to end up being relatively straightforward in the same way that inc and dec are. And then we've got like, I don't know where to go from there. We could start doing jump instructions maybe. These are 6 here, or sorry, 7. So I think that occupies the entire 7 row. So yeah, maybe jump conditional we can follow that with. Those are probably encoded somewhat differently, and certainly there's going to be other jumps around that are sort of one-off encodings. We had to deal with that already though with inc and dec and with the like add ADC, and like these also have a couple of variants that are elsewhere. I think they're this immediate group here, this grade section. So even in our very simple cases, and it applies to push and pop as well, there's like a few additional versions of those instructions that have just been fit in wherever, and that's just that's how they are. Push and pop here are, I'm not sure what I want to do with those yet. The name for the opcode, the mnemonic for it, is push and pop, but they don't work on a register. They are pushing or popping, a segment register. Let's see if we can find this in the general purpose list. But like, I don't think I have a structure in my output instruction structure. I don't think I have fields that can handle in like properly representing what this instruction does. It's my guess. Let's see what we have under push. Yeah, so it's like pushing a segment register onto the stack. And there are a couple ways to encode that. This is a 2-bit thing that determines which of these 4 segment registers are being pushed. And it's a pretty similar setup for pop as well. Yeah, and then because of the way that the 2-byte encoding prefix works, these particular ones need to be represented as a 2-byte value, it seems like. So I won't even get to those because I'm not doing the 2-byte stuff yet. But I don't know. I don't have, like, I mean, it should be pretty straightforward, right? I'll add an enum to represent each of the different segments, and then I can have a segment operand, which probably only applies to these instructions. I don't know if there are other instructions that are actually operating on segment registers. Guess we'll find out. But yeah, these are 1-byte instructions actually, so other than that, it would be pretty straightforward. But we're going to deal with these versions. So we've got the rows that I was highlighting on the table are this and this, where reg is 3 bits. So they'll all start with that. Whether it's push or pop depends on this being a 0 for push or a 1 for pop. And then reg is going to just encode a particular register. So we've actually had the same setup with increment and decrement. And yeah, this is pretty similar to increment decrement because we also have a 2-byte encoding where the the second byte rather is the mod RM with the 3 bits representing the what am I saying? 3 bits representing the opcode extension. That's the terminology. So we have already also done that for Inc and Dec. So I don't think there's anything particularly different here. I think we can go ahead and this will be the most straightforward thing to continue with. And then we also have an immediate variety for push, which obviously there's not an equivalent for pop. So we can go ahead and try to implement that, I guess. It's encoded a little bit differently, but I don't know, should be doable. I guess the question then is, S here should refer to sign extension. So does the S also imply that it is, where am I going here? if the sign extension bit is on, does that mean that it is going to expect a single byte that then gets sign extended? There's no W bit, at least how they've written it. Maybe they're simply incorrect in the documentation. But without a W bit, there's no explicit, like, make sure that the immediate data is 8 bits or whatever the current default 16 or 32 is. In our case, we're just going to assume 32 for right now. So let me throw this into Zydus just to get a feel for what this is. But I think this is, if we're going to tackle it at all, it's going to be the last piece out of the push and pop stuff that we're going to handle. So, but I'm curious. So we've got 6 and let's do 6 and 8 and then 6 and 10. So 6, 8 needs more data. And that accepts a 32-bit. 6A is okay. Yeah. So if we have the S bit on, that also means use 8-bit immediate data and always sign extended. So I guess the reason to not have the W bit is because the sign extension always happens. So you can't push a, like, yeah, you can't push an unsigned single byte value. So if you want to push FF, just as an example, it is going to push that. Oh, you know what? Okay, there's probably just no concept of pushing a single byte because it's going to go on the stack, and the stack would become misaligned or whatever. Like, they probably just, it doesn't make a lot of sense to be pushing a single byte. If you want to have a single byte, it's still going to take up 4 bytes on the stack. That seems like a reasonable explanation. So, okay, so it's just you can't push FF and not have it write all, sign extend, but that's fine. If you then address it as a single byte, you can get the low FF and it doesn't really matter. So, okay. That answers that question. So I guess that'll be what we do for this stream. Do push and pop, or as much of that as I can do. And before we start on that, I'm going to add the size information, the operand size. Oops. We have size. Yeah, so we do have op size. Where does op size come in? I think I just used that in the reg bits function. Like up here. Yeah, so that's fine. We just want to add it into mod rm and SIB operand types. Okay, and I guess we need to define that up here. Oh, why do I have 2? Whatever. Okay. So then I'm going to add it into my tests. and we'll watch them fail. Drop size. What do we expect this to be? This is an 8-bit on this register, so this should be size 8. Do we have size 8? No. What, size 08? Sure. Just do it that way. Okay, so next mod RM, this is a 32-bit register on the other operand. Same here. This is reg 8 on the other. Oh yeah, I forgot to ask, Linus didn't make Linux, what math stuff are you studying? This is probably 32-bit then. An 8-bit here. And here as well. And this one's going to be 32-bit immediate. And this one gets sign extended, so I'm gonna assume it's 32 bits. Did we do that already? Yeah, that's a D-word pointer, okay. All right, and so it is 32 bits. And 32 bits here, or no, 8 bits here, because it's AH. 8 bits here, and 8 bits here. This one's probably 32, yeah. It's the other register, this is 32 as well. 8. Okay, so these are, let's find out. Is this the one that I did at the beginning? No, didn't do this one. 84B21F. All right, this is a byte. This is a 32-bit. This is probably the one that I did. 8CB21F. Yeah. This one is a byte. This one is 32. Okay, so they all have size fields, and I'm going to add size unknown is 0, so that if we don't set it, then the test should fail. So we should get a bunch of failures, yeah. 7 passed, 23 failed. Think that feels right. So our zip or mem, except for these ones, but these are automatically, these are the mem ones, I'd say. Or no, these are register ones. So why did those fail? 603, oops, test. This was dec R8, or reg 8 rather, and it failed with the register was 0. Do I need to make clean and make test? No. Okay, rebuilt the test. So these should be referring to the correct field. Why is it getting 0 in the register now? That is confusing. I don't know why it's getting 0, but I think what we need to do is let's set the size field, which should fix the other tests that are expecting a particular size value, and maybe some of these other tests will stop failing. I don't know what the deal is. 369? Which is, that is a size one, but it got 24 for the size. Like something is being copied incorrectly or not zeroed out when it should be. And that's kind of frustrating. Oh, it could just be that like these are things that we're not zeroing them out from previous call. Is that in a loop? that one, 369, is in a loop. Maybe it's getting a value from, oh, okay, all these sib ones need to be sib.size. That's my bad. Too much copy paste. Okay. Is all set then? All right. Didn't fix anything, but I think, well, yeah, we're still getting, those ones are still wrong. In terms, I mean, it's not that I expected it to necessarily fix tests, but the expectation, like, why is it a value other than 0, basically, is confusing to me. Oh, and okay, I did the copy paste real bad. I'm realizing. So this is fine for operand 1, but this needs to be operand 2. Yeah, just really. And there's so, like, no, this should say op1. Okay, I think got those fixed. Then OT mod RM, because it's going to be similar problems here. Okay. So now we've got 0 as the failure value everywhere, I think. Yeah, we still, something is going on with these register ones that I don't yet understand. Because I must have copied these wrong as well. How did these not fail before? It must have been because there is because I'm using a union over all the operand types, and the first value in the mod RM and SIB, or at least the mod RM register, sorry, in the mod RM, operand type, the first field in that structure was a register. So that meant when we were doing a union of this and I was accessing the register field in it, it was effectively equivalent to having directly referenced this register, because I wanted it to be a register type operand, but I was accessing it through this structure, and they just happened to be overlapping memory that worked out properly, and that's why the test passed, but it was bad code. I wonder if that kind of poor, sloppy coding would be caught by Rust. It feels like the kind of thing that they would make their compiler be concerned with. But I don't know. I'm going to ask a friend real quick. All right, so I can make these .reg. Where are these other failures? 504. And 521. And 538. Oh no, that was a correct failure. 603. We didn't correct that one, I think. Jesus. Oh no, we did. Okay. And 620. And I think that's probably all of them. Okay, so now we have 19 failing tests, and none of them are register only. So that makes more sense. Okay. So now we just have to properly set the operand sizes. Okay, so I think the rule that we can probably follow is if the W bit is set, then the mod RM1 use the W4. We're only using W down here. Yeah, when it's a register. Okay. And I think if W, we say insert operand 2 dot mod rm dot so that's also a difficulty that I want to just set it on mod rm and then later set it on SIB, but I feel like that's continuing down the path of like bad coding. And we're already seeing the poor results of my bad coding. So I'm going to say op size and if it's W, or we can do it right here, I think, right? Okay. Then if we're an SIB, we can say operand2.sib.size equals op2 size. We'll do that for this one as well. Otherwise, it'll be on mod rm. Is that all of them? I think so. And now they all pass. So that, I guess that was hitting all of the cases that we needed to hit. So just yeah, the size of the mod rm is going to be based on the W bit. If it is off, then we're doing a byte pointer, and if it's on, then we're doing a pointer of the size that the machine is currently operating at, and we're just assuming 32 bits for right now. So cool. I will that's what I want to do. Okay. I wanna add these other fixes that were exposed by doing this. In their own commit. So then all right, cool. So we got all that going, and we can start working on the next instructions. Okay. So let's add pop is going to come in as, we'll do push and then pop. That will allow us to do something very simple for these instructions. It doesn't really help us on these guys because we've got 111, or sorry, we've got 110 versus 000 for the opcode extension bits, and then the high nibbles are different anyways. Yeah, I don't know why they couldn't arrange it so that they were both started with FF, but such is the results of, I don't know, I'm sure they had good reasons for it, or maybe it just didn't matter when they were doing it. So on the basis of one version of these instructions being a little bit simpler to encode, we'll go ahead and do that. I'll update the debug code, even though it doesn't get used right now. But it'll complain if we don't update it. Okay, so we've got push is, we're gonna do these guys first. So 0101 right in here. Okay. And these appear to be the only ones that start that way. So that's handy. Right, yeah, because they're the whole row. All right, so we need the high bit from the low nibble. So inster opcode is equal to op push plus opcode L and 8 shifted over 3. Exactly the same thing that we did for ink, actually. I was basically just retyping that just now, but I can make it 0x8 for a little bit of consistency. So yeah, we'll mask off and use that bit to determine if we're doing a push or a pop. And then the register stuff is going to be the same. And I'm going to go ahead and delete this because I want to write some tests for it first, actually. Test push alternative. Did I call it alternate? Alternate. You test pop alternates. Do we have a loop for the alternate ones? Yeah, we do. Okay, I'll copy the loop structure since these are very similar bits of code. Or sorry, they're very similar instructions. I think it's even just 5 instead of 4. But let's see. Let's copy these guys. And then we'll fix this up to say 4 instead. Okay, then down here, this will also be 5. If we do Zydus info of like 48, that's a, sorry, 58, that's a pop. And 54 should be a push. Yeah. Okay. So pop push. Got the register. That'll be a none. And pop. Okay. These should all fail. Cool. And now let's go ahead and implement it. Operand 1 dot type equals OT register. Operand 1 dot reg equals reg bits to enum w. Opcode L and 0x7. I want to say 0x7 here as well. True, and I guess it's 32 bits always with these. Okay, still failure. Interesting. Let's see, 678. The size. Yes. Return 1. Cool. Then, yeah, we got those in. Got rid of the easy ones, and now we can look at the more involved ones that actually do modRM and have this encoding. I wonder if this then has them in a group and we can do a function based on that group. I don't know if it makes any sense with these, but let's give it a look-see. So these will be 8F and these are FF. So we will look in our tables and we have 8F is the pop and FF should be the group here. So it's I guess there's a pop in or a push in here somewhere in group 5, and this is group 1A. So 1A just has pop all by itself. Interesting. And then, wow, I didn't notice the font difference here. It feels like it's yelling 111 at me. Anyways, group 5, the push is here with the 110. So, like, why not make the push here? Or really make this push and this pop? Because that would match the ordering where push is a 0 and pop is a 1. Like, what was their reasoning there? I don't know. Oh well. Oh, I don't know what I'm gonna do with these. It's just gonna be anybody's. All bets are off at this point because it seems to be saying if you have 11 in the mod bits, if you have 1 binary rather, 11 binary or whatever, then the opcode extensions are encoding these, and maybe these are the reg bits. And if you have one of the other values that's a mem value, I don't know. I don't want to get into it. I mean, this is where they've clearly been pushing the boundaries of how many instructions they can fit. Like to the point where they want every single, all 256 single byte opcode values to mean something. Not necessarily each an opcode, because you need escapes for like multi-byte opcodes and stuff, but they don't want to leave anything unused, and so they are just fitting stuff in. And these are actually ultimately 2-byte opcodes, just encoded really weirdly with the mod or m byte rather than a separate, having a prefix and then a second opcode byte or something. Ugh, whatever. Okay, I'm getting off track just looking at the shit show that this will eventually become. Not that it's particularly pleasant to look at right now. I think before I get into doing stuff like this, I'm going to start reviewing other people's implementations just to, like, as a cheat sheet for what is the most sane way I've seen anybody achieve this. Because right now I can't think of anything that would be sane, but I'm keeping to the most sane parts of it for the moment. So we're going to do 8. Would you already have some stuff in that portion of the if statement? And so we'll just add one that's looking at the low nibble for an F. And if we have pop, I wonder if it's like, yeah, because there's no other instructions that are at 8F. So it's only pop, but it's still only pop if you use 000 as the extension code. And then we'll throw push in there in the existing code that we're already using for Ink and Deck. So, okay, we can just update our existing group 1 with a group 1A little extra bit, I guess. Or maybe we just do a separate function for group 1A. And I think I will add some additional conditional stuff, into the group 4, 5 function that we already have. So I'm going to take a break for like a couple minutes, and then we'll come back and we'll do that.
Take it in real life like haiku. I know we got the good vibes when pieces fall right into place. Even if I lost all my money, the zero runs deep, honey. And I don't need to speak a single word, 'cause you got me holding it. Even if my jokes aren't funny, my tongue tied up on it. And I don't need to speak a single word, 'cause you got me holding, holding. I'm Jimmy at Woodstock. Drive me around in your red Ford. Shivers down my spinal cord. Oh, 'cause you got me holding, holding. Even if I lost all my money, the zero runs deep, honey. And I don't need to speak a single word, 'cause you got me holding, holding. Even if my jokes aren't funny, my tongue tied up on it. And I don't need to speak a single word, 'cause you got me holding, holding.
All right, we're back. And here we go. So 8F is going to be oh, these special. Yeah. Do we want to do this with how does that look in the table? 8. That is I see. Okay. Yeah. So we just want to say else if opcode L is equal to F. What do we need? What do we actually need for that version of pop? I think we just need the mod RM byte and should be okay. So we can send ixns +1 and instruction. Let's put it here. What is this? Oh, because it, yeah, whatever. Okay, So we'll return 2 because it's always going to be a 2-byte opcode. Is that true? No. It's always going to be 1 plus however many bytes from the mod RM, because that could certainly include displacement. Then we just want to say integer size plus equals decode mod RM x86. We'll dereference that, so just pass in that byte and false, I guess, or it's always going to be true for W in this case. I think so. Yeah, we're always going to be pushing or popping rather a 32-bit value, or what, 16-bit if it were in 16-bit mode, but we're never going to pop a byte. So W will be on x86 plus 1 and the instruction. And next stream maybe I should I'm going to delete all of this because I again did not start writing the test first, and I want to try to hold to that. But what was I saying? At some point I'm going to refactor the mod RM decode function to take 2 operand pointers rather than the instruction pointer, because it doesn't make sense for mod RM to be knowing which operand is which. And some of these instructions have them sort of in the opposite order from what we anticipate. So like basically the whole having to swap stuff doesn't make a lot of sense when we could just pass in those instructions in the opposite order, or more realistically we would pass one in and pass null for the other one, and mod RM wouldn't even bother setting that other one because this is a single, the other operand is an immediate. So yeah, we will do that another time though, maybe at the end of this stream. Okay, so this is where we were at. And let's write some tests for it. Utest pop, and we want a, I guess it's always a 32-bit register, yeah. So this really is the equivalent of that alternate encoding, because there's no way for us to be encoding a different kind of thing with the mod RM byte. So it's just a longer form of encoding this same instruction, which is honestly fine by me. And then I'm going to make these 2 per line just because we now have 2 bytes, so it's going to expand a little bit. And these are going to be 8F and then 12 and whatever, or C and whatever. Yeah. Replace that with 0x8F space, comma, space 0xC. think that makes sense. And these are for pop, right? So, but these need to be, I'm gonna use the push ones because we are actually from 0 through 7. Right? Yeah. Okay. That should be fine. This is going to be a 2-byte pop. And it's still a register. Okay. Then the memory ones are more involved for encoding, so I'm not going to do a loop with all of the varieties. I think just going to do something like this. How many of these do we have? Yeah, we'll just do this. Let's not do a big replace. Okay, so if we have an SIB with a 32-bit displacement, and it is 8-byte reference. Does that even make sense? No. Let's just do one test, I guess. That's fine. We can do an 8-bit displacement. It is a size of 32 because it ought to be a size of 32. And let's see, should be a 3. No, it's going to be a 4-byte instruction because SIB. So mod is going to be 01, I think, for SIB with a it's going to be 01, 00, and then 0100. Yeah. So just 44, and 8F to begin with. 8F, 44, and then we'll have to pick what these are. Just make this 56 just to have something a little bit different. And let's pick a different SIB. Oh, maybe I can go just straight up from here. Maybe that'll... No? Oh, it's this last one. Okay. There we go. That's what I should do. So we had D0, which is what, this one? Let's do A2. A2 is going to give us a none for the scaled index, and so we're going to have a scale of 0, I think. Maybe there's a scale none. No, I think I just had an integer for this, so we'll put a 0 in there. I think that's what it's going to expect, or what we have codified in our other tests. And then we'll have reg none for the index register and edx for the base register. Okay. Still have a displacement of 56. So that's A2. So if we do 8F44A2 56, that's going to come out as pop D-word pointer of EDX plus 56 hex. Yeah. D-word pointer EDX plus 56x. Excellent. Okay. Then, and that should be a register. Yeah. 4 bytes. So let's also throw the push. Just copy these two, and we'll put these under push. Okay, but they're gonna definitely be encoded differently. Might just be FF instead of 8F, but I think pretty sure the opcode extension bits are 110 instead, so we'll have to change the mod RM byte as well. Yeah, 110. So FF, and then for the register one, it's going to be F, and yeah. Okay, so like FF, F0, FF, F1, etc. And these are still 2-byte instructions that are push. I kind of like checking the instruction size earlier. Because if that's wrong, then we've probably decoded it wrong, and it might not be worth checking the whole rest of the thing. And certainly if that's wrong, then continuing on to the next instruction is just going to break stuff. So we probably should not keep going. We should error out as quickly as possible. And if the size isn't what we think it is, then that's the biggest signal that we're in an error condition. Okay, so it's going to be register, and yeah, we can keep with that. So I think this one is fine. Then we'll do, let's do just a classic mem with a 16-bit displacement. So we have 110 for the reg bits, that's fixed, and mod is gonna be, I think, 10, so 1011, so B, and then RM, we can sort of pick how we want that to go. And this will be a 5-byte instruction. Throw a D2 on there. this as a uint 16t. I don't know, we'll find out. It's gonna complain, and I'm not in the right headspace to be considering how to force it to interpret a certain literal. The displacement is always signed though, so maybe we can say treat that as a signed 16-bit. Okay, so if we are doing, so we don't have scale, we do have a size of 32 because it is still pushing. Yeah. Okay, so mod rm, and this is going to be a mod rm. Oops, not a swort. Just register, I guess. Figure out what the register is in a second. Let's see. If we do ESI, let's see if I can work out what these bits should be. Okay, so it's gonna be FF, and mod is 1011, so that's B, and then we've got 0, and ESI is, I think, 110. So try B6. And we've just got 2 bytes for the displacement. So it's still actually a 4-byte instruction. Yeah, so these bytes should say push D word pointer ESI plus D256, or like minus whatever the equivalent 2's complement is for that displacement. No. I thought B would be 10. Oh, no. It is, because 11 is register. So I guess you always have a displacement with a mod rm. So we do A6. No? God. And I thought I was getting better at this. Alright, well, let's look at... Oh, sorry, it's not going to be A6. right? It's going to be 0 what 0 1 1 1, so just 7 6. Push D-word pointer ESI plus 56. Huh, maybe you don't have a 16-bit displacement, I thought. Right. There's like a single code that you can do that gives you a 16-bit displacement, but then you don't have a register with it. It's my recollection now. No, there isn't even. Okay, never mind. I don't know where the 16-bit displacement, that's only available in 16-bit mode, I think. Yeah, okay. My brain was thinking of this table where you had no displacement and the 16-bit was in the 1 0. So you get no, 8, and 32 in this one. Okay, that's fine. Then we can have this as a 3-byte instruction. And then it's minus 2e. Okay. Cool. That seems like the right information. The operand size is still 32 because it's a D-word pointer. Yeah. Then we should have like 4 failing tests. Yeah, 4 tests failing. Okay, time to implement the first one, which is this one that I had started on. Else if opcode L is just F, we can return decode opcode group 1A. And we previously decided we only needed to pass in the pointer to the next byte and the instruction. So we have no flags for this. Const UNAT pointer, XNS, and instruction pointer. Okay. So we can say size t, inster size is 1 because we've got 1 for the opcode, and then inster size plus equals decode mod rm. We can pass in the next byte for that. True for w because it's always going to be 32-bit operand size. Pointer to the byte after mod rm, and then the instructions or instruction object pointer. And we want to do the swap stuff, I think. Instr operand 1 is going to set from operand 2 and memset okay. It's not morm, it's mod rm, mode rm. We want to return inster size for sure. Then is there anything else that we need to do? We just decode the mod rm byte and potential displacement and stuff, and I think that's everything. Okay, so that should get us both of the pop test push. failing or passing, but it does not. We didn't set the opcode. Okay, so now it's just the push tests that are failing. Cool. We can do those down here, I think. Else, do we want to turn this into a switch? Let's look at the extensions table again. So, where did it go? Oh, I clicked it, I guess, too far. Or is this the extensions table? No, this is the opcode map. Did I am getting myself lost. Okay, whatever. This is the one that we're looking at. So first we need to be sure that the opcode was actually FF, because we don't want to assume there's a push instruction here, because there is not. And the spec definitely says that these are reserved or whatever. They don't represent real instructions, so don't do anything for those. But we aren't actually defining that. Okay, then let's do like const unit constable group 4 is equal to flags. Right, the flags is just opcode L, so we can say flags. So it's either FE or FF. Oops. So if we have a E in the lower nibble of the opcode byte, then we're group 4. If we have an F, we're that. Okay. Oh, I see. So we just sort of checked the bits here. I guess that's fine. We can simplify this logic a little bit. We don't have to be quite so explicit and care about group 4 at all. And we can leave this as is because there's no extraneous one anymore. Okay. Then we can say group 5, sorry, if group 5. And you know what? We can just say flags is equal to 0xf right now. Because I guess the W bit doesn't matter. Oh, I see. It's basically like W is on in all of the F cases. I don't know if that would have any impact on call and jump though, but we won't worry about it for now. So let's say we're gonna switch on the extension. Case is going to be just 110. So this is going to be a push, and then insert size plus equals decode mod rm. True. I guess we can pass in w, it doesn't really matter. We'll copy this code because this does what we need. Right, we just swap it, and then size of operand. Yeah, I think this will work. Let's give it a shot. Did not work. So the memory displacement, what were we expecting on 722? The size should be 3. That is true. That is a 3 byte. And is that the only one that failed? No. Well, a different one failed now. 729. Okay. So what if we treat this as a uint? No. Oh, not a uint 16, but maybe an int 8. All right. So our test was a little bit wonky. Yeah. That makes sense. You know? The whole thing sort of builds on the existing logic for these groups, and we have a place where we can decode these couple of call and jump instructions. But you know, there's like bound to be call instructions in other places as well. I'm not even like I'm weirded out that some of these are lowercase. I don't know what's going on with VP straw. Or just, I guess, PSRAW, shift, packed data, write, arithmetic. So these are MMX and later sort of SIMD, I guess. Oh boy, I mean, implementing an emulator for this stuff would be just deeply annoying. I can see why so many projects use the so there's the Unicorn engine, which is a CPU emulator, but it is in fact based on QEMU. Although I'm curious when they talk about how it's beyond QEMU, I think they don't mean that it does more kinds of emulation. It is a little more flexible in how it emulates, but so you can use it as a library inside of other tools that don't need to do a full emulation of a entire, you know, CPU start to finish kind of thing, but you can emulate little bits, which is like Anger is built on top of Unicorn for some of its stuff, it seems like. And certain fuzzing things are built on top of it. But ultimately, the emulation logic is done in QEMU. And then there's also Box. And I feel like those are like, well, that's not how I would search for that. x86. So we've got box. There's a virtual x86. Curious about that. Yeah, let's see if Wikipedia has a list for us. Simnat, like, are these commercial? No. SPC, AT, and Q. Interesting. Then do we have x86 down here? Yeah. So obviously there's emulators that are like virtual machines, and these days I think they do their best not to have to emulate stuff, but they probably have some software emulation. But it just is like, oof, so many things to so many instructions once you start adding in all the SIMD extensions over the years. What is this? What is it running on? I see. So this is a software emulator. It's just up through Pentium 1. It's got the x87 FPU stuff. I guess it's mostly in JavaScript, or at least some of it's in JavaScript. And it's not going to be a exact emulator because it doesn't do 80-bit internal calculations. Yeah, and I mean, obviously, if you want to emulate a real computer, then you've got to emulate other hardware as well. It's just like so much stuff. Curious what they've got in here. Just one 5,000 line file of JavaScript. Yeah. And presumably there's a decoder in here somewhere. I don't know where, but maybe it's in another file. That would make the most sense. I don't know. I'm not going to look through all of it, but there's just not that many emulators for x86 because I think it's just straight up a whole lot of work because there's so many things in it. Nice. This one's somebody is going through the trouble of emulating the full thing with old VGA and stuff. Okay, and Q is like a port of QEMU, it seems like. Or it was. I guess it's not anymore, and maybe QEMU works on Mac now. I don't know, but that makes a little more sense. Spim. And I feel like there's probably a few other ones out there. Oh, this one's by AMD. That are just like somebody's GitHub project that maybe does a small portion of the instruction set. So cool. You can, if you're working on an OS and you need debugging capabilities, AMD has an emulator for you, or they did at one point. I guess they've just changed the URL. It should be a good wiki citizen or whatever. I'll have to log in to fix this, and I don't have an account, so I'll get to it afterwards. But yeah, certainly the folks at AMD working on this thing are, it's probably, what did it say, free and proprietary or something? Where was it? Freeware, yeah. So no source code for this guy. Not terribly surprising. But it is appreciated that they, have something out here, and it gives the impression that it would be fairly accurate, complete kind of thing. If it's coming from AMD, and probably has some level of internal usage by them as well. But pretty minimal on the hardware side of things, which is part of what'll, the thing with QEMU is it sort of like spans a lot of different use cases. If you can use it for something like binary analysis, but also, hey, you can just run a virtual machine for any purpose at all on it, that is a very broad set of use cases. And I don't know, it's just it definitely probably has its drawbacks in terms of how that software gets developed and designed, because it needs to meet all of these different needs, whereas this, nobody's going to use this to be running an OS that they are having software on for the purpose of running software in a virtual machine, a virtualized environment, or whatever. But it, it's more focused on people doing super low level software development, kernel development, that kind of thing, who need to be able to debug in a more sane fashion than what you would do if you're debugging on real hardware for the same purposes. So I think that's pretty cool. If I ever get around to making an operating system or something, trying out that side of things, then this is a tool that I'd probably make good use of. It'd probably be fun to work on a little bit fun. I don't know if it would be, just too annoying of an experience or what. Wonder if Emutopia, I guess they've got various other emulator. It's like an emulator database. Oh yeah, so we can see all these like small, in terms of user base and stuff, emulators, but people have worked on them over the years. I think that, it seems most likely that they've got early era x86 and not trying to emulate AVX and SSE 3 and all that stuff. Does homepage work at all? Yeah. Development sort of petered off about 4 years ago, but still, that's nice. Okay, enough putzing around. I am going to commit this stuff. And you know what? We might as well give that last push instruction give it a shot, and then I think I will try to fix up the decode mod RM and refactor that a little bit, because just copying that swap code every time is already making me feel like, ugh, why have I written code like this? So let's see. Oh, I didn't notice somebody came in and followed me. Cure Kill, thank you for the follow if you are by any chance still hanging about. Okay, boo, 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 boo. So we've got a 6 and either an 8 or an A. And then an immediate. This is probably not going to be encoded in any group stuff. So let's look. Probably don't need a separate function for it. It's going to be 6 on this. 6, 8, and 6A. Yeah. Cool. Let's commit this stuff. And then we're in here. Okay, so what we want, we'll just mask the go ahead and mask that low byte. So skipping the S bit, if 1 is the only, if the high bit is the only one set, then we've got to push. And we want to say answer opcode equals op push operand 1 dot type is just immediate. And then we can say if is an immediate, do we need a size on an immediate? I know in this case it's always 32-bit because I was talking about that earlier at the beginning of the stream. If you're pushing something to the stack, it's always going to push the sort of word size for the whatever mode the CPU is in. So in this case, 32 bits. But are there other cases where we'd have an immediate and there's no other operand, but it would need, like, we would need to also know the operand size? I mean, I won't deal with it now, but got mul, maybe imul would allow us to, That's an immediate. There's always two parameters with an immediate here, so I guess that doesn't matter. Yeah, maybe we just don't have anything that would include an immediate all on its own, and we wouldn't have another way of determining what the operand size is. So that's fine. I'm going too far. Okay, so if opcode L and shift that over 1 is equal to, or we just say if that. So if the S bit is set, then we're going to read a single byte. And we're going to do a uint, or no, we're going to do an int 32t of how do we do this with the immediate up here? Oh, right, we had to cast it as an int 8 pointer instead of a uint 8 pointer. And then we promote it. Okay. Where am I at? Otherwise, I think we can just treat the thing as a uint, because we aren't sign extending it. We aren't really extending it at all. We're just grabbing an additional 4 bytes. Oh, and then we can say return 2 or return 5. I mean, maybe this should be in its own function, but it is what it is for right now. This code is just ugly all over, so why not keep up with that? Yeah, so it's either 1 byte, the 1 byte immediate, or 1 byte with a 4 byte immediate. Okay, and I'm gonna just break with the pattern that I had of writing the test first. So then this one is S6. If it's on, it's an A. So I think that means this will be an immediate, and it is sign extended. So let's do A4. Sorry, 6A doesn't mean it's immediate. It's definitely immediate, but it is 30, it's an 8-bit immediate. And decode input to the output instruction. We're going to do 2 bytes for register size, start equal opcode up push, start equal operand type OT immediate output dot operand 1 dot type. And then this one's going to be int 32t of that. We'll repeat that, but for an immediate 32, which is going to be a 68, and then do like 87, 40, 21, and 0. Did I miss? No, that should be 4 bytes. So what did I do here? Oh, the 68 is not part of it. I could call this uint 32t. Okay, I guess we just always have to, whatever. And then this one should be 5. All right, and those pass. That's excellent. Of course, would always feel better if I had written the tests first and then saw it fail and then saw my code make it pass, but I feel decently about this being accurate right now. I felt that before, and we've definitely had bugs, so I should do best practices rather than just feel good about my code. All right, let us fix the decode mod rm. This guy is gonna take operands 1 and 2, and think if, so we're gonna just change this around. Ugh. But it's gonna be worth it, I'd say. So this is the stuff that basically always happens. Right, we always do, and I shouldn't delete that stuff. We always do the mod rm part, but there's a few scenarios where we don't actually have the other register. And so making that other register operand 1 doesn't make as much sense. So I don't want to pass a null and then the operand pointer for the second one. So I'm going to change this to operand 1. Okay. And then this guy, oops, didn't mean to go all the way to the end of the file. This guy we're going to do down here. And only if it's not a null pointer. Okay. Then let's find out where we're using it. So in here, we want to say, do we want to swap stuff? I think what we want to do is, what's the cleanest way to write this? Let's say operand pointer. Oh, this is the annoying case of, I'm like putting myself into this situation and then complaining about it as I do so. I'm not going to put myself into that situation. Just call it RM. Okay, so if D, then opreg is equal to inster operand 1 address, and op rm is equal to inster operand 2. So let me think about this. If D is true, then no, because I also switched that stuff around, right? Op reg op rm. If D is true, then we want the register stuff how do we want to do this? Okay, so operand 2 is always the one that will be a register. So we really should pass it in that order. Where this one is RM, so it could be register, could be memory. But maybe we need to make this 2 and 1 and 1 and 2. So if D is set, then the what we had before, operand 1 was the register, and so it becomes operand 2. That's if not D. So I did have it right. I just have like swapped too much stuff around. So if not D, so we're in here, then the register operand, which previously was always operand 1, becomes operand 2. And RM becomes operand 1. Okay, I think that's the right order. All right, so then for this stuff, we don't have an opreg. So we can just say inster operand 1 and null. And same here. Don't need that. Yeah, fuck it, why not? Okay, then same here. Only got the one operand. So set it, skip the reg stuff. And then lastly, here. Where is this? 78. What am I doing with this one? And 104. And then down here on 119, is that the other one? Okay. What's going on? Null pointer dereference. If it's an SIB. Can we just say like do puts? We don't have a puts, huh? Do I want to? We're gonna avoid logging stuff right now. It's bad practice, but I'm just gonna keep this as a very shitty piece of code until I rewrite it in Rust and try to do the right thing and have actual assertions and I don't know, maybe exceptions or something. yeah, we don't really have a way of handling this. One thing I could do is have this return true or false if it worked, and then we could check the result here and return 0, which is our like only way of signaling an error right now, but that feels also very hacky. So yeah, if we try to do, why do we do operand 2 in here? Why do we, oh, this should just be operand 1. That's okay. I mean, granted, it could also be like, maybe we should just do that just for safety's sake, but this should be operand 1 for sure. Didn't even stop to think, like, why are we decoding the SIB into operand 2? And now, if I take this out, I think Clang is smart enough to realize, like, hey, that's not, there's no null case because we're not statically passing null into anything for that. We could do like just abort there as well. All right, all the tests also pass, so feel okay about that. Gonna like temporarily, what is it, inster operand 1. Yeah, because that's our pointer there. Okay. And it's not that I don't want this, it's that I want like that. Okay. All right, so yeah. do it that way. Okay. I think that's going to be everything for this one. It's a little bit shorter of a stream. Deal with this elsewhere. But, yeah. I don't know. I don't know where to go next. We can look at the table, I guess, and come up with some ideas of instructions that are ripe for. I mean, yeah, we could do the jump stuff. I guess I can start looking at what those seem to be. It's the whole 7 row. So from the opcode decoding, the opcode portion, it's fine. Oh, JCC's up here. Okay. So it's 7, or we've got a 2-byte one. So it's all 8-bit displacement. And what is the TTT? That's the actual code, right? So we need to add another table, another enum rather, to represent these. And then there's an N, I guess, for whether it is not. Yeah. So, I mean, that should be pretty doable, actually. This one is reasonably laid out. There's no random reordering of stuff into other little bits. But there are some... It did look like there were a few jumps. Oh, it's the unconditional jumps that have, like, some of the... using the extension bits and all that. Because there's... more options, I guess. Yeah, it seems like you can't do a conditional jump to a register. Makes sense, I guess. There's, you just gotta have some limit somewhere in terms of what your instructions can decode. And that's not an unreasonable limit, I suppose. So, what? Oh, did it just time out? Cool. So that's all getting pushed. So yeah, on the next stream, we will implement this stuff and maybe start looking at some of these jumps. They don't seem terribly difficult or different from what we already have. These ones are already in one of the functions that we've implemented, and these are going to be very similar to this with a slight difference of encoding on the opcode byte. But yeah, why not? Why not get into some meaningful instructions with the jump stuff? And I think that'll come on Tuesday probably. So usually do this Tuesday, Thursday. So tomorrow I'm gonna try to continue with the Nightmare course and doing the binary exploitation practice that I've been working on for a while now. Still doing ROP stuff. And maybe it will go smoother this time than it did on Wednesday. And yeah, thank you all for watching. Seemed like there were a few people earlier, and appreciate that. If you're watching on the VOD, thanks as well. I'll be back tomorrow.
Get up, we want you to get on your feet. stand up, stand up.